Hi friends, you are watching Engineering Made Easy. I am Lalit Vasist. In this video, we will discuss the Faraday's law of electromagnetic induction. For this, we will use this simulator, and with the help of this simulator, we will understand all the basics of the Faraday's law of electromagnetic induction. So let's start. First of all, the main thing is, what is Faraday's law of electromagnetic induction? It is given as, if I see the formula, then it is given as the induced EMF E is given as E is equals to minus of N d phi by dt. I will explain all these terms. D phi by dt. Okay, what does this mean? Here E is the electromotive force. Okay, EMF, induced EMF, is equals to minus of N d phi by dt. Phi is the flux, okay, magnetic flux, and N is the number of turns in the coil. So what does this rule says? Actually, according to this, the electromotive force around a closed path is equal to the negative of the time rate of change of the magnetic flux enclosed by the path. It means, if we see it by this example, then here we have this voltmeter, and this is the coil, okay, and here is the bar magnet. So what will I do? I will change the position of this bar magnet, okay, and we'll see how it produces the induced EMF in this, and how this bulb lightens. So this is the Faraday's law of electromagnetic induction's formula, and according to this, the induced EMF, okay, it depends on the rate of change of flux in this coil, okay, and also on the number of turns of the coil. As the number of turns of this coil increases, the induced EMF increases. Not only this, as this rate d phi by dt means how the flux, the magnetic flux, is changing with respect to time. If d phi by dt is more, it means it is inducing more EMF. D phi by dt more means the change in flux is more with respect to time. If I, as let me show you it by these lines. These are the magnetic field lines. You see, here is the bar magnet, north pole, and here is the south pole, and all these lines are moving from, coming out from the north pole and entering into the south pole. See the direction of these field lines, magnetic field lines, okay, you can observe it. They are making a closed loop, okay. So as I move this bar magnet towards this, as you can see that magnetic field lines are associated with this bar magnet, and they are linked, they are cut by this coil. So if it is stationary, this bar magnet is stationary, or you can say there is no relative motion between these two, there between this coil and bar magnet, no voltage is induced, okay. But if I move it, then you see there is a change. So the change occurs only when there is a motion, relative motion, between this bar magnet and the coil, okay. So as I will increase the speed, okay, d phi by dt will increase because the rate of change of flux will increase. So on moving it fast, there will be more deflection in this voltmeter, the reading will be high, the induced EMF will be high. So, and if I move it slowly, then you see, if I'm moving it very slowly, then you see this voltmeter, okay, and the glow of this bulb, it will be small. You see, it is, there is little deviation, okay. But if I put it inside it and do not move it, so there is no relative change, there is no change in flux, the flux is constant at this point. So change in flux with respect to time means I need to vary it. So let's move it, whether I move it towards it, okay, let's see. From here I am moving it towards this coil, so it is having deflection. If it is going away, then it is having deflection in the opposite direction. If I'm taking it back, then again deflection, and it is moving outward from the other side, then there is deflection. But at this point, or if I put it at this point, or I put it at this point, whenever it is stationary with respect to this coil, no change in flux with respect to time, so no deviation, no glow of bulb, no voltmeter readings. Okay, so this was the concept. It also depends on the number of coils. You see how it depends. Let's take another example. Should I remove this formula? Let's close it. So you see here, I'm removing these field lines also for clarity. You see, I'm moving it with same speed towards the coil, and here it has 4 turns and here only 2 turns. As I told you that n d phi by dt, so n is the number of turns, it should be half actually. In this case n is half of this, only 2 turns, so it should be low. Let's keep the d phi by dt almost same manually. I'm trying my best. Let's see. Okay, this deflection, and if I do this same with this, then you see the deflection is more. Okay, so in this case the deflection will be double of that if d phi by dt is same, since n is double. In here it is 4, here it is 2 only. Another observation, so this was the related to n. Now let's see some other observations with this single coil only. See the direction of deflection. Here it is north pole towards its side, and if I increase, you see the deflection. Okay, as I move this bar magnet towards this coil. One more thing that you should understand here, that whether I move this magnet or the coil, there is no difference there. The important thing is the relative position, the relative change in these positions of the magnet and this coil. Okay, I can put this bar magnet stationary and can move this coil also, or I can move both of them, but at least there should be one moving thing, so that there should be change in the flux d phi by dt. Another way can be, if I put this magnet here, let's say it is inside this, and it is having a stationary magnetic field, so no change in flux, so there is no glow or no voltage induced EMF. But I have this bar magnet, or I can say there is any source of magnetic field that is producing variable magnetic field. In that case also, even there is no relative change in the positions of these two, but it is having some time variable magnetic flux. Okay, it is a source of a variable magnetic field, so in that case also there will be d phi by dt, rate of change of flux will be present, so EMF will be induced in that case also. Now we were seeing the direction of the deflection. Okay, you observe it carefully. Here it is the north pole. Towards it I can change it from this side. I can put the south pole at this side, but let's again put north pole in this side. Now observe it. If I will move it towards this coil, keeping north pole towards facing this coil, then you see what happens. The direction of this deflection, the deflection direction is in left side. You observed it. And when I will move this away from the other side, then see the deflection. Initially it was left, here it is in right. Okay, when it is moving away, it is in right deflection. Let's do the same experiment with the south pole. Okay, south pole facing it. Here it is north. Now let's take south here. The bar magnets pole, I have reversed them. Now see, initially the deflection was in left side when I was moving it towards it. Now see, the deflection is in right side. Okay, and when I will move it away from it, and see, deflection would be in left side. You observed deflection was in left side. So on changing the direction of poles, the deflection, the EMF induced direction is reversed. Okay, and also it is again reversed when we move it towards the coil or when we move it away from the coil. In that case also the direction is opposite. Okay, so I hope you got all these points and understood how the EMF induced depends on number of turns of the coil and the rate of change of magnetic flux, that is minus n d phi by dt. Okay, this is the induced EMF. And you also observed the negative sign in the formula, that is E equals to minus of n d phi by dt. It is according to the Lenz law, which says that if some EMF is induced, then this induced EMF will cause current in some direction. So this current will again produce the magnetic field, and this magnetic field's direction will be such that it will oppose original magnetic field that was responsible for its production. Okay, listen these words carefully. Okay, so I hope you got all these concepts. We demonstrated all these things. Okay, so I hope you liked the video. Please click on the like button and share it with your friends if you found it useful and liked it and enjoyed it. And do not forget to subscribe my channel Engineering Made Easy for more such interesting and informative videos. So thank you guys for watching this video till the end. See you soon in the next video with such more informative videos. Thank you for watching. Bye bye.